Welcome to SAML Federation Architecture. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into SAML Federation Architecture, one of the most important authentication and authorization frameworks used in modern enterprise environments. SAML stands for Security Assertion Markup Language, and it's an open standard that enables single sign-on capabilities across different domains and organizations. Understanding SAML is crucial for anyone working with cloud services, enterprise applications, or identity management systems. SAML Federation solves a critical problem in distributed systems. How do we allow users to authenticate once and then access multiple applications without having to log in repeatedly? Think about your work environment where you might log in once in the morning and then seamlessly access your email, customer relationship management system, human resources portal, and cloud storage without entering your credentials again. This seamless experience is made possible by SAML Federation. The fundamental concept behind SAML is the establishment of trust relationships between different parties. There are three main actors in any SAML transaction. First, the user or principal who wants to access a resource. Second, the identity provider, who authenticates the user and vouches for their identity. And third, the service provider, who hosts the application or resource the user wants to access. The identity provider and service provider establish a trust relationship beforehand, exchanging metadata and cryptographic certificates that allow them to verify each other's authenticity. Throughout this presentation, we will explore the architecture of SAML Federation, understand the detailed flow of authentication assertions, examine the XML structure of SAML messages, and learn about practical implementation considerations. We will also look at how SAML compares to other authentication protocols like OAuth and OpenID Connect, and discuss security best practices for deploying SAML in production environments. By the end of this session, you will have a comprehensive understanding of how SAML enables secure, federated identity management across organizational boundaries. SAML core components and actors. Let's begin by understanding the three fundamental components that make up any SAML Federation architecture. These actors work together in a carefully orchestrated dance to enable secure authentication and authorization across organizational boundaries. Each actor has specific responsibilities and communicates with the others using standardized SAML protocols. The first and most important actor is the principal, also commonly referred to as the user or subject. This is the person or entity attempting to access a protected resource or application. The principal initiates the entire SAML flow by attempting to access a service. The principal typically uses a web browser as their user agent, which facilitates the communication between the other actors. The principal does not need to understand SAML protocols themselves. The browser handles all the redirects and form submissions automatically. The second actor is the identity provider, often abbreviated as IDP. The identity provider is the system that authenticates the user and creates SAML assertions about that user's identity and attributes. Think of the IDP as the authoritative source for user identity within an organization. Common examples include Microsoft Active Directory Federation Services, Okta, Azure Active Directory, Ping Identity, and OneLogin. The identity provider maintains user credentials, manages authentication policies, and generates digitally signed SAML assertions that attest to the user's identity and entitlements. The third actor is the service provider, abbreviated as SP. The service provider is the application or service that the user wants to access. Instead of maintaining its own user database and authentication system, the service provider delegates authentication to the identity provider. The service provider trusts the identity provider to correctly authenticate users and relies on the SAML assertions it receives. Examples of service providers include Salesforce, AWS, Google Workspace, ServiceNow, and countless other cloud applications. The service provider's role is to consume SAML assertions, validate them, and grant access to authenticated users. The trust relationship between the identity provider and service provider is established before any authentication flows occur. This setup phase involves exchanging metadata documents that contain information about each party's endpoints, supported bindings, cryptographic certificates, and protocol capabilities. The metadata exchange ensures both parties can properly communicate and verify each other's messages. The cryptographic certificates enable digital signatures and encryption, ensuring that SAML assertions cannot be tampered with or read by unauthorized parties during transit. SAML Authentication Flow Overview. Now that we understand the actors involved, let's examine how a typical SAML authentication flow works from start to finish. SAML supports multiple profiles and bindings, but we will focus on the most common scenario: the service provider initiated flow using HTTP redirect binding. This is the pattern you encounter most frequently in real-world deployments. The flow begins when a user attempts to access a protected resource on the service provider. For example, imagine a user navigating to their company's Salesforce instance. The service provider recognizes that the user is not authenticated and needs to verify their identity. Instead of presenting a local login form, the service provider generates a SAML authentication request, also called an authn request. This request is an XML document that specifies what information the service provider needs from the identity provider. The service provider then redirects the user's browser to the identity provider's single sign-on service endpoint. This redirect includes the SAML authn request, typically encoded and embedded in the URL as a query parameter. The HTTP redirect binding allows this information to be passed through the user's browser without requiring any browser plugins or special client software. The browser automatically follows the redirect, effectively delivering the authentication request to the identity provider. When the identity provider receives the authentication request, it first checks if the user already has an authenticated session. If the user previously logged in and their session is still valid, the identity provider can skip the credential verification step. If not, the identity provider presents a login page where the user enters their username and password or uses multi-factor authentication. The identity provider validates these credentials against its user directory, which might be Active Directory, LDAP, or a cloud-based user store. After successful authentication, the identity provider creates a SAML response containing one or more SAML assertions. These assertions are XML documents that make statements about the user's identity, attributes, and authorization decisions. The identity provider digitally signs these assertions using its private key, ensuring their integrity and authenticity. The service provider can later verify these signatures using the identity provider's public certificate, which was exchanged during the initial metadata setup. The identity provider then sends the SAML response back to the service provider. Using HTTP POST binding, the identity provider creates an HTML form that contains the SAML response in a hidden field and automatically submits this form back to the service provider's Assertion Consumer Service URL. The browser performs this POST operation, delivering the SAML assertion to the service provider. The service provider validates the signature, checks the assertion's validity period, extracts the user's identity and attributes, and finally grants the user access to the requested resource. From the user's perspective, this entire complex exchange happens almost instantaneously. SAML assertion structure and components. Let's dive deeper into the structure of SAML assertions, which are the core payloads that carry authentication and authorization information. A SAML assertion is an XML document that follows a specific schema defined by the SAML specification. Understanding this structure is crucial for troubleshooting SAML implementations and ensuring proper security. Every SAML assertion contains several key elements. At the root is the assertion element itself, which includes attributes like the assertion ID, issue timestamp, and version number. The ID must be globally unique, and is typically a randomly generated string. The issue timestamp indicates when the identity provider created the assertion, which is critical for enforcing time-based validity. SAML 2.0 is the current version, and is specified in the version attribute. The issuer element identifies who created the assertion. This is typically the entity ID of the identity provider, which is a unique identifier often formatted as a URL or URN. The service provider uses this issuer information to determine which certificate to use when verifying the assertion's signature. This ensures that only assertions from trusted identity providers are accepted. The signature element contains the digital signature that protects the assertion's integrity. This signature is created using XML signature standards and typically uses RSA-SHA 256 or stronger algorithms. The signature covers the entire assertion, meaning any modification to the assertion would invalidate the signature. The signature element includes references to the identity provider's certificate, signature algorithm, and the canonicalization method used before signing. The service provider must validate this signature before trusting any information in the assertion. The subject element identifies the principle that the assertion is about. It contains a name ID element that specifies the user's identifier in a format agreed upon by both parties. Common name ID formats include email address, persistent identifier, transient identifier, or Windows domain qualified name. The subject also typically includes a subject confirmation element that specifies how the recipient can confirm that the assertion applies to the current request. The bearer subject confirmation method is most common, indicating that possession of the assertion is sufficient proof. The conditions element specifies constraints under which the assertion is valid. This includes not before and not on or after timestamps that define the assertion's validity window. These timestamps help prevent replay attacks where an attacker might try to reuse an old assertion. The conditions also include an audience restriction element that specifies which service providers are allowed to consume this assertion. The service provider must check that its own entity ID is listed in the audience restriction. Finally, the assertion can contain three types of statements. An authent statement describes the authentication event, including when and how the user was authenticated. This might indicate whether the user used a password, multi-factor authentication, or certificate-based authentication. An attribute statement contains user attributes like name, email, department, or group memberships. These attributes allow the service provider to make authorization decisions and personalize the user experience. An auth's decision statement contains authorization decisions, though this is less commonly used in modern implementations where authorization is typically handled by the service provider itself. SAML bindings and profiles. SAML is flexible enough to work with different transport mechanisms and use cases. This flexibility is provided through the concepts of bindings and profiles. Bindings define how SAML protocol messages are transported between actors, while profiles define specific use cases and message flows. Understanding these concepts is essential for implementing SAML correctly in different scenarios. Let's start with SAML bindings. A binding specifies how SAML messages are mapped onto standard communication protocols like HTTP. The HTTP redirect binding is one of the most commonly used bindings. In this binding, SAML protocol messages are transmitted via HTTP redirect operations, typically using GET requests. The SAML message is deflated, base 64 encoded, and URL encoded before being appended to the redirect URL as a query parameter. This binding is simple and doesn't require any special client support, but it has size limitations since URLs can only be so long. The HTTP redirect binding is primarily used for auth-n requests from service providers to identity providers. The HTTP POST binding is another widely used binding, especially for SAML responses containing assertions. In this binding, SAML messages are base 64 encoded and transmitted via HTTP POST operations. The identity provider generates an HTML form with the SAML message in a hidden form field and uses JavaScript to automatically submit the form. This binding can handle much larger messages than the redirect binding and is the standard way that identity providers send assertions back to service providers. The POST binding also provides better security since the SAML message is in the HTTP body rather than the URL, which may be logged by intermediary systems. The HTTP artifact binding provides an alternative approach where instead of passing the actual SAML message through the browser, only a reference or artifact is passed. The artifact is a small token that the service provider can use to retrieve the actual SAML assertion directly from the identity provider using a back-channel SOAP request. This binding is more complex but offers advantages in terms of confidentiality since the assertion never passes through the user's browser. It's particularly useful when assertions contain sensitive information or when the assertion size exceeds what can be practically transmitted through a browser. The SOAP binding is used for back-channel communication between the service provider and identity provider. This binding is not user-facing. Instead, it is used for direct server-to-server communication. For example, in the artifact binding scenario, the service provider uses SOAP to request the full assertion from the identity provider. SOAP bindings are also used for single logout scenarios where the identity provider needs to notify multiple service providers that a user has logged out. Now let's discuss SAML profiles, which define specific use cases and workflows. The web browser SSO profile is the most important and widely deployed profile. This profile describes how a user with a web browser can authenticate at an identity provider and access a service provider's resources. The profile supports both service provider-initiated flows, where the user accesses the service provider first, and identity provider-initiated flows, where the user starts at the identity provider's portal and selects which service to access. The single logout profile defines how to terminate sessions across multiple service providers when a user logs out from one location. This is more complex than it sounds because the user might have sessions with multiple service providers, and all of these need to be terminated to achieve a proper single logout. The identity provider typically orchestrates this process, sending logout requests to all service providers where the user has active sessions. Metadata exchange and trust establishment. Before any SAML authentication can occur, the identity provider and service provider must establish a trust relationship. This is accomplished through the exchange of SAML metadata documents. Understanding metadata is crucial because improper metadata configuration is one of the most common sources of SAML integration failures. A SAML metadata document is an XML file that describes the capabilities, endpoints, and security configuration of either an identity provider or service provider. The metadata serves as a contract between the two parties, specifying exactly how they will communicate. Both the identity provider and service provider publish their metadata, and each party imports the other's metadata into their configuration. This exchange can be done manually by downloading and uploading XML files, or automatically by providing a metadata URL that the other party can fetch. The identity provider metadata contains several critical pieces of information. First, it includes the entity ID, which is a globally unique identifier for the identity provider. This is typically formatted as a URL, even though it does not need to be a resolvable address. The entity ID is used by service providers to identify which identity provider an assertion came from. The metadata also includes the single sign-on service endpoints, specifying the URLs where the identity provider accepts authentication requests. Different URLs might be provided for different bindings, for example, HTTP redirect and HTTP post. Most importantly, the identity provider metadata contains the X.509 certificates that the service provider needs to verify signatures on SAML assertions. These are the public certificates corresponding to the private keys the identity provider uses for signing. The metadata may include multiple certificates to support key rollover scenarios where the identity provider is transitioning from an old certificate to a new one. The metadata also specifies which name ID formats the identity provider supports, which authentication contexts it can provide, and which SAML bindings it supports. The service provider metadata similarly contains the entity ID uniquely identifying the service provider. It includes the Assertion consumer service endpoints, which are the URLs where the service provider expects to receive SAML responses. Multiple endpoints might be listed, each potentially supporting different bindings or serving different purposes. The metadata specifies whether the service provider wants assertions to be signed, whether it wants entire responses to be signed, or both. This is important because the security requirements can vary based on the service provider's risk assessment. Service provider metadata may also include attribute consuming service information, which describes what user attributes the service provider needs or wants to receive in SAML assertions. This helps the identity provider know what information to include in the assertions it creates. For example, a service provider might require email address and display name but also request optional attributes like phone number or department. The metadata can also specify logout endpoints for single logout support and public certificates if the service provider needs to sign its authentication requests or decrypt encrypted assertions. The process of exchanging metadata typically happens during the initial setup phase of a SAML integration. Some identity providers and service providers have user interfaces where you can upload metadata files or provide metadata URLs. Others require manual configuration, where you extract information from the metadata and enter it into configuration screens. Once metadata is exchanged, and both parties have configured their trust relationship, they can begin exchanging SAML messages securely. It is important to note that when certificates are updated, the metadata must be exchanged again to maintain the trust relationship. Service provider initiated flow in detail. Now let's walk through a complete service provider initiated authentication flow step by step, examining exactly what happens at each stage. This is the most common SAML flow, and understanding it in detail will help you troubleshoot issues and implement SAML correctly. Step 1 occurs when the user attempts to access a protected resource on the service provider. For example, the user navigates to https://mycompany.salesforce.com in their browser. The service provider checks if the user has an existing authenticated session. This is typically done by checking for a session cookie. If no valid session exists, the service provider knows it needs to redirect the user to the identity provider for authentication. In step 2, the service provider generates a SAML authn request. This XML document includes the service provider's entity ID so the identity provider knows who is making the request. It includes an Assertion consumer service URL specifying where the identity provider should send the response. The request may include a name ID policy specifying what format of user identifier the service provider wants to receive. It might also include requested authn context to specify the desired authentication method, such as requiring multi-factor authentication for sensitive applications. The authn request is assigned a unique ID that will be referenced in the response to prevent replay attacks. Step 3 involves encoding and transmitting the authn request. If using HTTP redirect binding, the XML is deflated using DEFLATE compression, then base 64 encoded, then URL encoded. The encoded request is appended to the identity provider's single sign-on URL as a SAML request query parameter. Additional parameters might include relay state, which is an opaque string the service provider can use to maintain state across the redirect, allowing it to send the user to the right location after authentication completes. The service provider issues an HTTP 302 redirect response to the user's browser with the location header pointing to the identity provider's SSO URL with the encoded SAML request. In step 4, the user's browser follows the redirect and lands on the identity provider's single sign-on endpoint. The identity provider decodes the SAML request and validates it. It checks that the request came from a known and trusted service provider by looking up the issuer in its metadata. It validates that the assertion consumer service URL matches what's registered in the service provider's metadata, preventing attacks where a malicious actor might try to redirect assertions to their own endpoint. The identity provider extracts the relay state parameter if present and stores it for later. Step 5 is where user authentication occurs. The identity provider checks if the user already has an authenticated session, perhaps from logging into another application earlier. If a valid session exists and meets the authentication context requirements specified in the authentication request, the identity provider can skip credential verification. If not, the identity provider presents a login page. The user enters their credentials, which might include username and password, smart card, biometric authentication, or multi-factor authentication tokens. The identity provider validates these credentials against its user directory. In step 6, after successful authentication, the identity provider creates a SAML response containing one or more assertions. The response element includes an in-response to attribute that references the ID from the authn request, binding the response to the specific request. The assertion includes the user's name ID in the format requested by the service provider. It includes an authn statement documenting when and how authentication occurred. It includes an attribute statement with any user attributes the service provider requested or that are configured to be sent. The identity provider applies the conditions element with not before and not on or after timestamps, typically giving the assertion a validity window of a few minutes. It adds an audience restriction specifying the service provider's entity ID. Step 7 involves signing the assertion. The identity provider computes a cryptographic hash of the assertion XML using a secure hash algorithm like SHA-256. It then encrypts this hash with its private key, creating a digital signature. This signature is embedded in the assertion within the signature element, along with references to the certificate containing the corresponding public key. The signature ensures that any modification to the assertion would be detectable. Some configurations require signing both the assertion and the entire response for defense in depth. In step 8, the identity provider prepares to send the response back to the service provider using HTTP post binding. It base64 encodes the SAML response XML. It generates an HTML document containing a form with the encoded response in a hidden field named SAML response. If there was a relay state, it is also included as a hidden field. The form's action attribute points to the service provider's assertion consumer service URL. The HTML includes JavaScript that automatically submits the form when the page loads. The identity provider sends this HTML document to the user's browser. Finally, in step 9, the user's browser executes the JavaScript, submitting the form and posting the SAML response to the service provider. The service provider receives the response and validates it thoroughly. It base64 decodes the SAML response parameter. It verifies the signature using the identity provider's public certificate that was exchanged in metadata. It checks that the in-response to attribute matches the ID of the authn request it sent. It validates the timestamps in the conditions element to ensure the assertion is still valid. It verifies that the audience restriction includes its own entity ID. It checks the assertion hasn't been seen before to prevent replay attacks. After all validation succeeds, the service provider extracts the user's name ID and attributes, creates a local session for the user, sets a session cookie, and redirects the user to the originally requested resource or to the URL specified in the relay state parameter. The entire flow completes, and the user is now authenticated and can access the service provider's application. Identity provider initiated flow. While service provider initiated flows are more common, many organizations also use identity provider initiated flows, especially when they maintain a central portal where users start their day. In this flow, users log into the identity provider first and then select which application they want to access. Let's examine how this flow differs from the service provider-initiated approach. The flow begins at the identity provider rather than the service provider. The user navigates directly to the identity provider's portal, often something like login.mycompany.com or an enterprise portal page. The identity provider presents a login page, and the user authenticates with their credentials. After successful authentication, the identity provider presents a dashboard or portal page showing all the applications the user has access to. These might be displayed as tiles or links representing different service providers like Salesforce, Office 365, AWS Console, and internal applications. When the user clicks on one of these applications, the identity provider initiates the SAML flow. Unlike the service provider-initiated flow, there's no authn request to respond to. The identity provider knows which service provider the user wants to access based on which link was clicked. The identity provider looks up the metadata for that service provider to determine the Assertion consumer service URL and other necessary configuration details. Since the user is already authenticated, the identity provider immediately creates a SAML response. The assertion in an identity provider-initiated flow is very similar to one in a service provider-initiated flow. It contains the subject identifying the user, conditions specifying validity period and audience restrictions, an authentication statement, and attribute statements. The key difference is that the response element does not include an in response to attribute because there was no request to respond to. This has security implications that we will discuss shortly. The identity provider generates the same HTML form with the base 64 encoded SAML response and automatically submits it to the service provider's Assertion consumer service endpoint using HTTP post binding. The service provider receives this response, validates it, and establishes a session for the user. Since there's no relay state in an identity provider-initiated flow, the service provider typically redirects the user to a default landing page rather than a specific resource. The identity provider-initiated flow offers advantages in terms of user experience. Users can bookmark their identity provider portal and have a single starting point for all their applications. They authenticate once and can then access multiple applications without additional login prompts. This centralized approach makes it easier for IT departments to communicate with users about where to go and provides a consistent experience. It also makes it easier to implement features like recently used applications or application search functionality. However, the identity provider-initiated flow has security considerations. Because there is no in response to attribute binding the response to a specific request, the flow is more vulnerable to attacks. An attacker who can intercept or steal a SAML assertion could potentially replay it to gain unauthorized access. Service providers need to implement additional safeguards, for example, strict assertion lifetime enforcement and potentially tracking assertion IDs to prevent replay. Additionally, the lack of relay state means that deep linking to specific resources within applications is more challenging. Many organizations use a hybrid approach, supporting both flows depending on the use case and application requirements. SAML attributes and attribute mapping. One of SAML's powerful features is the ability to pass user attributes from the identity provider to the service provider. These attributes enable rich personalization and authorization capabilities without the service provider needing its own user directory. Let's explore how attributes work, common attribute types, and the challenges of attribute mapping. Attributes in SAML are included in attribute statement elements within assertions. Each attribute has a name format that specifies how to interpret the name, and one or more values. The attribute name might be something like email, given name, surname, or department. The name format provides context for interpreting the attribute name. Common name formats include URI format, where the attribute name is a URI like earn, OID, 0.9.2342.19200300300.100.1.3 for email, or basic format for simple string names. Common user attributes passed via SAML include identity attributes like email address, username, and user ID. These identify the user and are often required for the service provider to establish a session. Profile attributes like given name, surname, display name, phone number, and job title enable personalization of the user interface. Group membership or role attributes indicate what groups or roles the user belongs to, which the service provider uses for authorization decisions. Department, location, and cost center attributes might be used for analytics or access control based on organizational structure. The challenge with SAML attributes is that different systems use different attribute names and formats. Your identity provider might call something email address while a service provider expects mail or email. This is where attribute mapping comes in. The identity provider typically has configuration capabilities to map attributes from its user directory to the attribute names expected by each service provider. For example, you might map the mail attribute from Active Directory to an email attribute with URI name format for one application, and to a different attribute name for another application. Attribute mapping happens at assertion creation time in the identity provider. When creating an assertion for a specific service provider, the identity provider looks up the attribute mapping rules configured for that service provider. It queries its user directory for the necessary attributes about the authenticated user. It applies any transformation rules, such as concatenating first and last names to create a display name, or converting a binary group membership attribute to a human-readable group name. It then includes the mapped attributes in the attribute statement using the names and formats the service provider expects. Some identity providers support dynamic attribute resolution and attribute release policies. Instead of statically configuring which attributes to send to each service provider, these systems can make runtime decisions based on policies. For example, a policy might say to only send the department attribute to service providers that have a specific tag in their metadata, or to only send phone numbers to applications marked as requiring multi-factor authentication. This provides more flexible and maintainable attribute management in large federated environments. Service providers must be configured to understand and use the attributes they receive. This often involves mapping the incoming SAML attributes to internal user profile fields. For example, a service provider might map the SAML email attribute to its internal user.email field and the SAML group's attribute to internal role assignments. Some service providers provide user interfaces for this mapping configuration, while others require editing configuration files or using APIs. Incorrect attribute mapping is a common source of integration problems, especially when users do not get the expected access rights or when their profile information appears incorrect in the application. Security considerations and best practices. Implementing SAML securely requires attention to multiple security aspects. While SAML is designed with security in mind, improper configuration or implementation can create vulnerabilities. Let's examine the key security considerations and best practices for deploying SAML in production environments. The most critical security control in SAML is the digital signature on assertions. Always require signed assertions, and some organizations also require signed responses for defense in depth. The signature ensures that assertions have not been tampered with and come from the claimed identity provider. Use strong signature algorithms like RSA-SHA 256 or better. Older algorithms like RSA-SHA 1 should be avoided as they have known weaknesses. The key length matters too. Use at least 20 48-bit RSA keys, with 40 96-bit keys preferred for high security environments. Certificate management is crucial for maintaining the trust relationship. BY.509 certificates used for signing have expiration dates, and you need a process for certificate rotation before they expire. Many identity providers support publishing multiple certificates in their metadata. with one marked as the current signing certificate and others as future certificates. This allows service providers to trust assertions signed with either certificate during a transition period. Plan certificate rotations well in advance, typically starting the transition at least 30 days before the old certificate expires. Test with multiple service providers to ensure they all properly support the new certificate. Assertion lifetime should be kept short to minimize the window of vulnerability if an assertion is intercepted or stolen. A typical assertion lifetime is 5 minutes, though this can be adjusted based on risk tolerance and network latency considerations. The not before and not on or after conditions enforce this lifetime, and service providers must strictly validate these timestamps. Be aware of clock skew between systems. Allow a small time window, perhaps 1 to 2 minutes, to account for time synchronization differences between the identity provider and service provider. Both parties should use NTP to maintain accurate system time. Always validate the audience restriction in assertions. The audience restriction element should contain the service provider's entity ID, and the service provider should reject assertions that do not include it. This prevents stolen assertions intended for one service provider from being replayed to a different service provider. Similarly, service providers should validate the in response to attribute in service provider initiated flows to ensure the response corresponds to a request they actually made, preventing injection attacks. Implement replay prevention mechanisms. Service providers should track assertion IDs they have processed and reject any assertion with an ID they have seen before. This tracking only needs to cover the assertion lifetime period. Once an assertion has expired based on its timestamps, its ID can be removed from the tracking store. Some service providers implement this using a cache with time-based expiration, while others use database tables with periodic cleanup jobs. Transport layer security is essential even though SAML provides message-level security through signatures. Always use HTTPS for all SAML endpoints. This protects against eavesdropping and ensures that entire SAML messages, including any potentially sensitive user attributes, are encrypted in transit. Use modern TLS versions like TLS 1.2 or TLS 1.3 with strong cipher suites. Disable older protocols like Secure Sockets Layer 3.0 and TLS 1.0 which have known vulnerabilities. Consider encryption of assertions in addition to signatures when dealing with highly sensitive user attributes. While signatures protect integrity and authenticity, they don't provide confidentiality. The HTTP POST binding transmits assertions through the user's browser, and while HTTPS encrypts the transport, the assertion could potentially be logged or cached by browser extensions or proxy servers. SAML supports encryption where the identity provider encrypts the assertion using the service provider's public key, and only the service provider can decrypt it with its private key. This adds complexity but provides stronger confidentiality guarantees. Implement proper logout mechanisms. Single logout is more complex than single sign-on because it requires coordinating session termination across multiple service providers. The logout must be secured to prevent logout request forgery, where an attacker tricks the identity provider into logging out a legitimate user. Logout requests should be signed and validated. Consider user experience as well. If a user closes their browser without explicitly logging out, their identity provider session might persist, potentially allowing another user on the same computer to access their applications. Implement session timeouts to mitigate this risk. Single logout architecture. Single logout, often abbreviated as SLO, is the counterpart to single sign-on that ensures when a user logs out from one application, they are logged out from all applications in the federation. While single sign-on is relatively straightforward, single logout presents significant architectural challenges because it requires coordinating session termination across multiple independent service providers. Understanding these challenges and the solutions SAML provides is crucial for implementing secure federated identity systems. The fundamental challenge with single logout is this: When a user authenticates using SAML, they end up with multiple sessions across different systems. They have a session with the identity provider, created upon their initial authentication. They also acquire separate sessions with each service provider they access, established when each service provider consumes a SAML assertion. These sessions are independent and managed by different systems. So, when the user clicks logout, we need a mechanism to terminate all these sessions to prevent unauthorized access. SAML supports two main single logout profiles: the front channel logout profile and the back channel logout profile. The front channel profile uses the user's browser to propagate logout messages between parties, similar to how authentication requests and responses flow through the browser. The back channel profile uses direct server-to-server communication, typically via SOAP, to notify service providers of logout events. Each approach has advantages and limitations that affect reliability and user experience. In the front channel logout profile, when a user initiates logout at a service provider, that service provider sends a logout request to the identity provider through the user's browser using HTTP redirect or HTTP POST binding. The identity provider receives this logout request and terminates the user's session. The identity provider then needs to notify all other service providers where the user has active sessions. It does this by redirecting the browser to each service provider in sequence with a logout request. Each service provider terminates its local session and acknowledges the logout by redirecting back to the identity provider. After all service providers have been notified, the identity provider redirects the browser to a logout completion page. The challenge with front channel logout is reliability. Since logout messages flow through the user's browser via redirects, the process can be interrupted if the user closes the browser window, if network connectivity is lost, or if any service provider in the chain fails to respond promptly. This can leave some sessions active even though the user intended to log out. Additionally, the serial nature of front channel logout means the process can take a noticeable amount of time if the user has sessions with many service providers, creating a poor user experience as the browser bounces between multiple systems. The back channel logout profile addresses some of these reliability concerns by having the identity provider notify service providers directly via SOAP messages over persistent HTTP connections. When a user initiates logout, the service provider sends a logout request to the identity provider. The identity provider terminates its session and then makes direct SOAP calls to the logout endpoints of all service providers where the user has active sessions. These back-channel notifications happen independently of the user's browser, so they are not affected by the user closing windows or network issues on the client side. The service providers terminate their sessions and respond to the identity provider with acknowledgement messages. However, back-channel logout has its own challenges. It requires that service providers expose SOAP endpoints that are accessible from the identity provider's network, which can be problematic in scenarios involving cloud services or network segmentation. The identity provider needs to maintain state about which service providers the user has active sessions with, which requires session tracking infrastructure. There's also no guarantee that all back-channel notifications will succeed immediately, so identity providers typically implement retry logic and timeout mechanisms. Some implementations use a hybrid approach, attempting back-channel notification but falling back to front-channel methods for service providers that don't support back-channel SOAP endpoints. SAML versus OAuth 2.0 and OpenID Connect. As we discuss SAML Federation, it is important to understand how it compares to other modern authentication and authorization protocols, particularly OAuth 2.0 and OpenID Connect. These protocols are often mentioned together, but they serve different purposes and have different design philosophies. Understanding when to use each protocol helps architects make informed decisions about identity federation in their environments. SAML was designed in the early 2000s primarily for enterprise single sign-on scenarios. Its design reflects the needs of that era. XML-based messaging, comprehensive feature sets covering authentication and authorization, strong support for attributes and federation metadata, and profiles optimized for web browser-based applications. SAML provides a complete framework for federated identity, including detailed specifications for authentication, attributes, authorization decisions, metadata exchange, and single logout. The protocol is mature and widely deployed in enterprise environments, particularly for integrations between corporate identity providers and business-to-business SaaS applications. OAuth 2.0, in contrast, was designed as an authorization framework rather than an authentication protocol. OAuth 2.0 enables applications to obtain limited access to user resources on another system without exposing user credentials. The canonical use case is allowing a third-party application to access your Google Drive files or post to your Twitter account without giving the application your Google or Twitter password. OAuth 2.0 introduces the concept of access tokens that grant specific permissions for specific durations. The protocol uses JSON rather than XML and is designed to be simpler and more developer-friendly than SAML. A critical distinction is that OAuth 2.0 alone does not provide authentication. It tells you what an application is allowed to do, but it does not reliably tell you who the user is. This led to developers misusing OAuth 2.0 for authentication in ways that introduced security vulnerabilities. OpenID Connect was created to address this gap. OpenID Connect is an authentication layer built on top of OAuth 2.0 that adds standardized ways to verify user identity. It introduces ID tokens, which are JSON web tokens containing claims about the user's identity and authentication event. OpenID Connect provides endpoints for user authentication, token validation, and user information retrieval. From an architectural perspective, SAML and OpenID Connect both solve the single sign-on problem but with different approaches. SAML assertions are typically larger XML documents that can contain extensive attribute information. They are designed to be passed through browsers with strong digital signatures protecting their integrity. OpenID Connect ID tokens are more compact JSON structures, often transmitted as JWTs that can be easily parsed by modern web applications. Both protocols support similar flows, like service provider-initiated and identity provider-initiated authentication, though the terminology differs. The choice between SAML and OpenID Connect often depends on the integration context and ecosystem. SAML dominates in traditional enterprise scenarios, especially for B2B integrations where the service provider is another enterprise organization. Many enterprise SaaS applications like Salesforce, ServiceNow, and Workday have mature SAML implementations and may not support OpenID Connect. Corporate identity providers like Active Directory Federation Services and Ping Federate have extensive SAML capabilities that have been refined over years of deployment. When integrating with these systems, SAML is often the pragmatic choice. OpenID Connect is increasingly popular in modern cloud-native applications, mobile applications, and API-driven architectures. Its JSON-based tokens integrate naturally with modern web frameworks and mobile development platforms. The protocol's design aligns well with microservices architectures where services need to validate tokens quickly without calling back to the identity provider. Major cloud identity providers like Azure Active Directory, Auth0, and Okta support both protocols, but their OpenID Connect implementations often provide better developer experiences with clearer documentation and more extensive SDK support. For new greenfield projects, especially those involving mobile or single-page applications, OpenID Connect is often recommended. Some organizations run hybrid environments supporting both protocols. The identity provider might expose both SAML and OpenID Connect endpoints, allowing different applications to use the protocol that best fits their needs. This requires maintaining configurations and integrations for both protocols but provides flexibility. The choice isn't always either or. Understanding both protocols and their strengths allows architects to select the right tool for each integration scenario. SAML error handling and troubleshooting. Despite careful implementation, SAML integrations frequently encounter errors during setup and operation. Understanding common error patterns, how to diagnose them, and where to find relevant information is essential for anyone working with SAML federations. Let's explore the most common SAML errors, their causes, and systematic troubleshooting approaches. One of the most frequent errors is signature validation failure. This occurs when the service provider cannot verify the digital signature on a SAML assertion. The root cause is usually a mismatch between the certificate the identity provider uses to sign assertions and the certificate the service provider has configured to verify those signatures. This often happens during initial setup, when certificates are not correctly exchanged via metadata, or during certificate rotation, when the new certificate has not been properly deployed to all service providers. The error message typically indicates signature validation failed or certificate verification failed. To troubleshoot signature validation failures, first verify that the identity provider's metadata has been correctly imported into the service provider configuration. Extract the X.509 certificate from the identity provider's metadata and compare it to what is configured in the service provider. They must match exactly, including any whitespace or line breaks. Check whether the identity provider has recently rotated certificates and whether the service provider needs to be updated with the new certificate. Some identity providers support publishing multiple certificates in metadata to facilitate transitions, so verify the service provider recognizes all valid certificates. Audience restriction violations are another common error category. The service provider rejects an assertion because the audience restriction element doesn't contain the service provider's entity ID. This typically indicates a configuration mismatch where the identity provider and service provider disagree on what the service provider's entity ID should be. Entity IDs are case-sensitive and must match exactly, so even a trailing slash or HTTP versus HTTPS difference will cause failures. The error message usually states that the audience restriction is not satisfied or the service provider is not an intended audience. To fix audience restriction errors, verify the service provider's entity ID and its metadata matches what is configured in the identity provider. Check for common issues, such as differences in URL schemes, trailing slashes, or domain name variations. Some service providers use different entity IDs for different environments, such as development, staging, and production. Therefore, ensure you are configuring the correct entity ID for the environment you are working with. Update the identity provider's configuration to include the correct entity ID in assertions sent to this service provider. Time-based validation errors occur when assertions are rejected due to not before or not on or after condition violations. The service provider considers the assertion either not yet valid or already expired based on the timestamps in the conditions element. This is often caused by clock skew between the identity provider and service provider servers. If the server's clocks are out of sync by more than the allowed tolerance, usually a few minutes, time-based validations will fail. The error message typically indicates the assertion is expired or not yet valid. To resolve time-based errors, first verify that both the identity provider and service provider servers are using NTP to synchronize their clocks. Also, check the actual time on both systems and their configured time zone settings. Most SAML implementations allow you to configure a clock skew tolerance, typically 2 to 5 minutes, to accommodate minor time differences. Verify these tolerance settings are appropriate for your environment. Additionally, check that assertion lifetimes configured in the identity provider are reasonable. These are typically 5 minutes, but can be potentially longer if network latency is high. Metadata errors manifest during the initial setup phase. These occur when metadata documents are malformed, do not validate against the SAML schema, or contain configuration errors. Common issues include incorrect endpoint URLs, missing required elements, invalid certificate formatting, or namespace errors. Some metadata problems only surface when the integration is tested, such as specifying bindings that are not actually supported or pointing to non-existent endpoints. When diagnosing metadata errors, validate the metadata XML against the SAML schema using an XML validator tool. Systematic troubleshooting of SAML issues requires visibility into the actual SAML messages being exchanged. Browser-based SAML debugging tools, like the SAML Tracer browser extension, capture HTTP traffic and decode SAML messages, allowing you to see the actual authn requests, responses, and assertions. These tools show the base 64 decoded and decompressed SAML XML, making it easy to inspect all elements and attributes. Identity providers and service providers often have debug logging capabilities that can record SAML messages. However, these need to be enabled carefully, as they may log sensitive information. When troubleshooting, work systematically through the SAML flow. Verify the authn request is correctly generated and contains appropriate parameters. Check that it reaches the identity provider and is properly decoded. Verify authentication succeeds at the identity provider. Examine the generated assertion to ensure that it contains all required elements with correct values. Verify the signature is present and uses the expected certificate. Check that the response reaches the service provider's assertion consumer service. Finally, verify the service provider successfully validates all aspects of the assertion. This methodical approach helps isolate where in the flow problems occur. SAML in multi-cloud and hybrid environments. Modern enterprise IT environments increasingly span multiple cloud providers and on-premises infrastructure. Implementing SAML federation in these hybrid and multi-cloud scenarios introduces additional complexity around network connectivity, trust boundaries, and operational management. Let's explore architectural patterns and best practices for SAML in distributed environments. In a typical multi-cloud scenario, an organization might use AWS for compute workloads, Azure for enterprise applications, Google Cloud for data analytics, and maintain on-premises Active Directory for identity management. Each cloud provider offers its own identity services. AWS IAM Identity Center, formerly known as AWS SSO, Azure Active Directory, and Google Cloud Identity. The challenge is enabling seamless authentication across all these platforms while maintaining a single source of truth for user identities. One common pattern is using an on-premises identity provider that federates to all cloud platforms. Active Directory Federation Services, or a third-party identity provider like Okta or Ping Identity, serves as the central authentication authority. User credentials and attributes remain in the on-premises directory. Each cloud platform is configured as a SAML service provider, importing the identity provider's metadata and establishing a trust relationship. When users access cloud resources, they are redirected to the on-premises identity provider for authentication. After successful authentication, the identity provider issues SAML assertions that grant access to the requested cloud service. This hub-and-spoke model provides several advantages. There is a single place to manage user identities, enforce authentication policies, and implement security controls like multi-factor authentication. Users have a consistent authentication experience regardless of which cloud platform they are accessing. IT teams maintain visibility into authentication events centrally. However, this architecture creates a dependency on the on-premises identity provider. If it becomes unavailable due to network issues or system failures, users cannot authenticate to any cloud services. Organizations must ensure high availability through redundant identity provider servers, reliable network connectivity, and proper disaster recovery procedures. An alternative pattern is using a cloud-based identity provider as the hub. Azure Active Directory, Okta, or Auth0 serve as the central identity authority. Your on-premises Active Directory then synchronizes user accounts to the cloud identity provider using tools like Azure AD Connect or Directory Sync agents. Cloud services integrate directly with the cloud identity provider via SAML. This pattern reduces dependency on on-premises infrastructure and provides better resiliency since cloud identity providers typically have higher availability than on-premises systems. The trade-off is that user credentials and potentially sensitive attributes now exist in cloud systems, which may have compliance or security policy implications. Chaining or proxying SAML federations is sometimes necessary in complex enterprise architectures. For example, a business unit might have its own identity provider that needs to federate with the corporate identity provider, which in turn federates with cloud service providers. In this scenario, the business unit's identity provider acts as a service provider to the corporate identity provider but as an identity provider to end services. These multi-hop federation chains require careful configuration of trust relationships and entity IDs at each level. Assertion mapping and attribute transformation may be needed to translate between different naming conventions used by different identity providers. Network connectivity is a critical consideration in hybrid SAML deployments. Identity providers and service providers need reliable network paths between them for SAML flows to complete successfully. Authentication requests and responses flow through user browsers, so client-to-server connectivity is essential. Back-channel communication like artifact resolution and single logout SOAP calls require direct server-to-server connectivity. Organizations must ensure proper firewall rules, DNS resolution, and TLS certificate validation across network boundaries. Split-tunnel VPNs and zero-trust network architectures add complexity by potentially routing traffic through different paths than expected. Operational management of SAML federations in multi-cloud environments requires discipline and tooling. Metadata management becomes more complex with multiple service providers across different platforms. Certificate rotation must be coordinated across all federation participants, requiring advanced planning and careful execution. Monitoring authentication flows and detecting failures across distributed systems requires centralized logging and alerting. Some organizations implement SAML proxy or gateway solutions that provide a single management plane for federations across multiple clouds, simplifying configuration and providing unified visibility. Compliance and data residency requirements may dictate where SAML assertions can be processed and what user information can be transmitted across cloud platforms. Some regulations require that authentication data remains within specific geographic regions or that certain attributes are not shared with third-party cloud providers. SAML's attribute release policies and assertion encryption capabilities help address these requirements. Organizations must carefully design their federation architectures to comply with applicable regulations while still enabling required functionality. Just-in-time provisioning and account lifecycle. A powerful feature of SAML federation is just-in-time provisioning, often abbreviated as JIT provisioning. This capability allows service providers to automatically create user accounts on first login based on information in SAML assertions, eliminating the need for manual account creation or separate user provisioning processes. Let's explore how JIT provisioning works, its benefits, and the considerations for implementing it effectively. In traditional user provisioning models, before a user can access an application, someone must explicitly create an account for them in that application. This might involve an administrator using the application's user management interface, running scripts that call provisioning APIs, or using identity governance solutions that sync users from a central directory to applications. These processes require advanced planning, introduce delays between when access is needed and when it is available, and create administrative overhead. JIT provisioning eliminates these steps by creating accounts automatically during the SAML authentication flow. Here is how JIT provisioning works in practice. When a user authenticates via SAML for the first time, the identity provider sends an assertion containing not just the user's identity but also attributes, for example, their email address, first name, last name, department, and potentially group memberships or role assignments. The service provider receives this assertion and checks if an account already exists for this user based on the name ID or another unique identifier. If no account exists, the service provider automatically creates one, populating the user profile with attributes from the SAML assertion. The user is then authenticated into this newly created account and can begin using the application immediately. The primary benefit of JIT provisioning is operational efficiency. Users can access applications immediately upon receiving access approval at the identity provider level, without waiting for separate provisioning processes to complete. IT administrators do not need to create accounts manually or maintain complex provisioning workflows for every application. When new employees join the organization, simply adding them to the identity provider and appropriate groups gives them immediate access to all authorized applications. This dramatically reduces onboarding time and administrative burden. JIT provisioning also helps maintain consistency between the identity provider and service providers. Since user attributes are sourced from SAML assertions on every login, updates to user information at the identity provider automatically propagate to service providers. If a user's email address changes, their department changes, or their role changes, these updates flow to applications through SAML assertions. Some service providers support updating existing accounts with current attribute values from assertions, not just creating new accounts, ensuring profile information stays synchronized. However, JIT provisioning has limitations and considerations. The service provider can only provision what is in the SAML assertion, so the identity provider must be configured to include all necessary attributes. This requires careful attribute mapping to ensure everything the service provider needs is present. Some applications have complex user models with relationships between objects that cannot be fully represented in SAML assertions. For example, assigning users to specific teams, projects, or organizational hierarchies may require additional provisioning steps beyond what JIT can accomplish. Account lifecycle management beyond creation is another consideration. JIT provisioning handles account creation automatically, but what about updates, deactivation, and deletion? When a user is removed from the identity provider or loses access to an application, JIT provisioning alone does not automatically deactivate or delete their service provider account. Some service providers implement timeout-based deactivation, where accounts become inactive if there is no authentication for a certain period. Others require explicit provisioning integration using protocols like SCIM system for cross-domain identity management to handle account lifecycle beyond initial creation. The timing of attribute updates varies by implementation. Some service providers only update user attributes during JIT provisioning at account creation time. Subsequent attribute changes in the identity provider won't update existing accounts. Other service providers support attribute updating on every authentication, synchronizing user profiles with current assertion values. Understanding and configuring this behavior is important for maintaining accurate user information. Organizations must document which attributes are JIT provisioned, how often they update, and whether any attributes require separate provisioning mechanisms. Security considerations around JIT provisioning include controlling who can create accounts. If anyone who can authenticate at the identity provider automatically gets an account in the service provider, unauthorized users might gain access. Most implementations allow configuring conditions for JIT provisioning, such as requiring membership in specific groups or the presence of specific attributes in assertions. This prevents arbitrary account creation while still enabling automatic provisioning for authorized users. Role and permission assignment during JIT provisioning is critical. New accounts should have appropriate access levels based on assertion attributes, not default to excessive permissions. SAML federation in mobile and native applications. While SAML was designed primarily for web browser-based single sign-on, modern applications often need to support mobile apps and native desktop applications. These platforms don't have the same browser capabilities that SAML relies on, creating challenges for implementing SAML authentication. Let's explore the options and patterns for enabling SAML federation in mobile and native application scenarios. The fundamental challenge is that SAML flows depend heavily on HTTP redirects and form posts. These mechanisms work seamlessly in web browsers, but they are problematic in mobile applications. A native mobile application cannot easily perform the browser redirects that move users between the service provider and identity provider. Additionally, SAML uses XML processing and cryptographic operations that are more complex to implement in mobile environments when compared to JSON-based protocols. The user experience of switching between the application and a browser for authentication can feel disjointed. One common pattern is the embedded browser or web view approach. The mobile application embeds a web browser component that can handle SAML redirects. When authentication is needed, the app opens a web view, navigates to the service provider's SAML authentication endpoint, and allows the SAML flow to proceed within this embedded browser. The web view handles all redirects between the service provider and identity provider, presents the identity provider's login page, and processes the SAML response. Once authentication completes, the application extracts session information or tokens from the web view and closes it, returning the user to the native application interface. However, embedded browsers have significant security and usability limitations. From a security perspective, embedded browsers do not share the system browser's credential storage, so users cannot benefit from saved passwords or existing identity provider sessions. The app has full control over the embedded browser's contents, potentially allowing malicious apps to intercept credentials through keylogging or screen capture. Modern security guidance recommends against embedded browsers for authentication flows. From a usability perspective, users must re-enter credentials in every app since sessions are not shared, creating friction and poor user experience. The current best practice is to use the system browser for SAML authentication through mechanisms like AS Web Authentication Session on iOS or Chrome Custom Tabs on Android. The mobile app initiates authentication by launching the system browser with the service provider's authentication URL. The system browser handles all SAML redirects and presents the identity provider's actual authentication page in a trusted environment. Since this is the real system browser, users benefit from any existing identity provider sessions and can use its password management features. After authentication completes, the browser redirects to a custom URL scheme or universal link registered by the app, allowing the app to receive the authentication result and continue. Implementing system browser-based SAML authentication requires careful coordination of redirect URLs and session management. The mobile app must register a custom URL scheme, like myapp:/, or use universal links that map to both the app and a web endpoint. The service provider must be configured to accept these mobile-specific redirect URLs as valid assertion consumer service URLs. The application needs to handle scenarios where the system browser redirect doesn't successfully return to the app, providing fallback mechanisms or user guidance. An alternative pattern is using a gateway or proxy that translates between SAML and mobile-friendly protocols. The mobile app authenticates using OAuth 2.0 or OpenID Connect, which have better mobile support with native flows and JSON-based tokens. A federation gateway or broker sits between the mobile app and the SAML-based service provider. The mobile app authenticates to the gateway using OAuth/OIDC. The gateway then handles SAML authentication to the actual service provider on the app's behalf, translating between protocols. The gateway returns OAuth access tokens or OIDC ID tokens to the mobile app, which uses these for subsequent API calls. This gateway approach provides better mobile developer experience since OAuth and OIDC have extensive mobile SDK support and familiar patterns. The app does not need to understand SAML or handle XML processing. However, it introduces an additional component that must be operated and secured. The gateway becomes a critical piece of infrastructure that must properly validate tokens, securely store SAML trust relationships, and correctly translate authentication state between protocols. Organizations often use API management platforms or identity proxies that include this translation capability as a standard feature. For native desktop applications, similar challenges and patterns apply. Desktop apps may have slightly more flexibility in hosting embedded browser components, but the security and user experience concerns remain. Modern desktop applications increasingly use similar patterns to mobile apps, launching the system default browser for SAML authentication and handling redirects back to the application through custom protocol handlers or local loopback URLs. Cross-platform frameworks like Electron, which essentially embed a full browser engine, can handle SAML flows more naturally but must still address session management and secure token storage. Performance optimization and scalability. As SAML federations grow to support thousands or millions of users across numerous service providers, performance and scalability become critical concerns. Understanding the performance characteristics of SAML flows and implementing appropriate optimizations ensures good user experience and system reliability at scale. Let's examine the performance considerations and optimization strategies for SAML federations. The SAML authentication flow involves multiple network round trips. The user's browser must redirect from the service provider to the identity provider. The identity provider processes authentication, and then the browser posts the response back to the service provider. Each of these redirects takes time, particularly if the identity provider and service provider are geographically distant or if network latency is high. The cumulative effect of these round trips is that SAML authentication typically takes several seconds from start to finish, even when everything is working optimally. Reducing the number of authentications required is the most effective performance optimization. The identity provider should maintain long-lived sessions so users only need to authenticate once per day or longer, not on every application access. When a user accesses multiple SAML-enabled applications, they should only see the identity provider login page the first time. Subsequent accesses should complete with just the browser redirects, using the existing identity provider session. This requires proper session management at the identity provider with appropriate session timeouts, secure session cookies, and session storage that can scale to handle millions of concurrent sessions. Service providers should also maintain session state efficiently. After successfully validating a SAML assertion, the service provider creates a local session for the user, typically tracked via a session cookie. This session should last for a reasonable duration, potentially hours or a full workday. The service provider should not require re-authentication with every request, or when a user navigates away from the application. Session storage needs to be fast and scalable. High-traffic service providers often use distributed cache solutions like Redis or Memcached for session storage rather than database-backed sessions. XML processing performance matters in SAML implementations. Parsing XML, validating schemas, and computing digital signatures are computationally intensive operations. Identity providers creating thousands of assertions per second and service providers validating thousands of assertions per second need efficient XML processing. Using optimized XML libraries, enabling just-in-time compilation for XML processing code, and potentially using hardware acceleration for cryptographic operations can significantly improve throughput. Some implementations cache parsed metadata to avoid repeatedly parsing the same XML documents. Signature validation is one of the most expensive operations in SAML processing. Every SAML response validation requires verifying a digital signature using RSA or ECDSA cryptography. These operations are CPU-intensive. Service providers under heavy load should consider several optimizations. First, ensure you are using efficient cryptographic libraries that take advantage of CPU instruction sets like AES-NI second. Consider using ECDSA signatures instead of RSA where supported. ECDSA signatures are faster to verify. Third, implement proper caching so that if the same assertion is somehow validated multiple times, subsequent validations can be short-circuited if safe to do so. Network latency between the identity provider and service provider affects user-perceived performance. While SAML messages flow through the user's browser, eliminating direct network dependencies between parties, the geographic distance between the identity provider and service provider still matters. If a user in Asia accesses a European service provider that redirects to an identity provider in North America, the accumulated latency from multiple transcontinental round trips creates noticeable delay. Organizations with global user bases should consider deploying identity provider infrastructure across multiple regions to reduce latency. High availability and load balancing are essential for production SAML deployments. Identity providers must handle authentication requests from all users across all integrated service providers, making them potential bottlenecks. Deploy identity providers in clusters with load balancers distributing traffic across multiple servers. Use health checks to ensure load balancers only send traffic to healthy instances. Implement failover mechanisms so if one identity provider instance fails, others seamlessly handle the load. Session affinity may be necessary depending on how session state is managed. Some architectures require that subsequent requests from the same user go to the same identity provider instance. Monitoring and observability are crucial for maintaining performance at scale. Instrument SAML flows to track authentication latency, success rates, and failure patterns. Monitor key metrics like average authentication time, 95th percentile authentication time, authentication throughput, and error rates. Set up alerts for anomalies like sudden increases in authentication failures or latency spikes. Distributed tracing can help identify where time is spent in multi-hop flows, such as whether delays are in network transit, identity provider processing, or service provider validation. This visibility enables quick identification and resolution of performance issues. Advanced SAML security features. Beyond the basic security mechanisms we discussed earlier, SAML includes several advanced security features that provide additional protection in high-security environments or address specific threat models. Understanding these advanced capabilities helps security architects design robust federated identity systems. Let's explore encryption, enhanced authentication contexts, and other advanced security features. Assertion encryption provides confidentiality for SAML assertions beyond what transport layer security offers. While HTTPS encrypts data in transit between the browser and servers, the SAML assertion itself passes through the user's browser where it could potentially be logged by browser extensions, cached by the operating system, or captured by malware. Encrypted assertions address this threat by having the identity provider encrypt the entire assertion using the service provider's public key before sending it. Only the service provider, with the corresponding private key, can decrypt the assertion. This ensures that even if the assertion is intercepted or extracted from browser memory, its contents remain confidential. Implementing assertion encryption requires that service providers generate encryption key pairs and publish the public certificate in their metadata. The identity provider imports this certificate and uses it to encrypt assertions destined for that service provider. The encryption typically uses XML encryption standards, often with AES for symmetric encryption of the assertion content and RSA for encrypting the symmetric key. The service provider's assertion consumer service decrypts the assertion using its private key before processing it. Encryption adds computational overhead and complexity, so it is typically reserved for scenarios involving highly sensitive user attributes or strict confidentiality requirements. Authentication context classes provide a way for service providers to request, and for identity providers to assert, the strength of authentication. Different authentication methods have different security levels. Password-only authentication is weaker than multi-factor authentication with a hardware token. SAML defines standardized authentication context classes that represent different authentication strengths, such as password authentication, password with protected transport, multi-factor authentication, and smartcard authentication. Service providers can specify a required authentication context in their authentication request. and identity providers include the actual authentication context in assertions. This capability enables risk-based or adaptive authentication policies. A low-risk application might accept password authentication, while a high-risk application, like financial transactions, requires multi-factor authentication. The service provider specifies the minimum required authentication context in its SAML configuration. If the identity provider's current session does not meet this requirement, the identity provider must re-authenticate the user with a stronger method before issuing an assertion. This allows centralized authentication policy enforcement while giving service providers control over their security requirements. The authentication context mechanism also supports step-up authentication scenarios. A user might authenticate initially with a password for basic access, establishing an identity provider session with password authentication context. Later, when accessing a sensitive application that requires multi-factor authentication, the service provider requests a higher authentication context. The identity provider recognizes that the current session doesn't meet this requirement and prompts the user for additional authentication factors like a one-time password or biometric verification. After successful step-up authentication, the identity provider issues an assertion with the higher authentication context. Holder of key subject confirmation adds an additional binding between the SAML assertion and the entity presenting it. In standard bearer assertion scenarios, whoever possesses a valid assertion can use it until it expires. Holder of key subject confirmation requires that the subject proves possession of a cryptographic key associated with the assertion. The identity provider includes a key identifier or the public key itself in the assertion's subject confirmation. The service provider requires that the subject prove possession of the corresponding private key, typically through TLS client certificate authentication or signed requests. This prevents stolen assertions from being useful to attackers who do not possess the required cryptographic key. SAML proxying and delegation scenarios enable complex trust relationships where intermediaries are involved. In a proxy scenario, a user authenticates to one identity provider, which acts as a service provider to another upstream identity provider. The downstream identity provider vouches for the user's identity to service providers based on assertions it receives from the upstream identity provider. This enables federation chains across organizational boundaries. Delegation scenarios allow a user to grant a service provider the authority to act on their behalf with other service providers, enabling service-to-service authorization flows. Enhanced replay prevention beyond basic assertion ID tracking includes additional mechanisms, for example, one-time use assertions and binding assertions to specific client information. One-time use conditions in assertions explicitly state that the assertion should only be consumed once. This requires service providers to track and reject any repeated use. Binding assertions to client information, for example, IP address or TLS session information, adds context that service providers can validate. This ensures assertions are used from the expected client context. These mechanisms provide defense in depth against sophisticated replay attacks. SAML implementation best practices. Successfully implementing SAML federation requires attention to numerous details across security, operations, and user experience. Drawing from years of production deployments, let's examine a comprehensive set of best practices that help ensure SAML implementations are secure, reliable, and maintainable. Start with thorough planning and documentation before implementing any SAML integrations. Document the trust relationship, including which system acts as identity provider and which as service provider. Record entity IDs, endpoint URLs, and certificate information for both parties. Create network diagrams showing how SAML flows traverse your network architecture. Document attribute mappings specifying which attributes flow from identity provider to service provider and how they are mapped. Maintain runbooks for common operations like certificate rotation and troubleshooting steps for frequent issues. This documentation becomes invaluable for ongoing maintenance and troubleshooting. Certificate management deserves special attention due to its critical security role. Use separate certificates for SAML signing versus other purposes like TLS. This isolation limits the impact if a certificate is compromised. Generate certificates with appropriate key lengths. Use 2048-bit RSA keys at minimum, preferring 4096-bit for high-security environments. Set certificate expiration dates far enough in the future to avoid frequent rotations but not so far that certificate management becomes lax. 2 to 3 year validity periods strike a good balance. Implement automated monitoring that alerts well before certificates expire, ideally 90 days before expiration. This provides ample time to generate new certificates, test integrations, and coordinate updates across all Federation partners. When rotating certificates, use a staged approach that maintains availability. Most identity providers support publishing multiple certificates in metadata, with one marked as active and others as pending or rollover certificates. Begin the rotation process by generating a new certificate and publishing both old and new certificates in metadata. Notify all service provider administrators about the upcoming rotation. Wait several weeks for service providers to import the updated metadata. Only after confirming all service providers recognize the new certificate should you start signing assertions with it. Keep the old certificate published in metadata for another grace period in case any service providers haven't fully transitioned. This cautious approach prevents widespread authentication failures. Security hardening goes beyond the basic SAML security mechanisms. Implement defense in depth by combining SAML's message-level security with network-level and application-level security controls. Always use HTTPS for all SAML endpoints with modern TLS versions and strong cipher suites. Implement rate limiting on authentication endpoints to mitigate denial of service attacks. Use WAFs to detect and block malicious SAML messages. Implement comprehensive audit logging that records all authentication events, including both successes and failures, with enough detail to investigate security incidents. Store logs securely with appropriate retention periods that satisfy compliance requirements. Testing SAML integrations thoroughly before production deployment is essential. Create test plans that cover normal authentication flows, error scenarios, and edge cases. Test service provider-initiated flows and identity provider-initiated flows if both are supported. Test authentication failures to verify error messages are appropriate and do not leak sensitive information. Test single logout to ensure sessions terminate correctly. Test attribute mapping to verify service providers receive expected user attributes. Test certificate validation by attempting to use assertions signed with incorrect certificates. Test time-based validations by manipulating system clocks to create expired assertions. Automated testing frameworks can execute these test cases repeatedly, catching regressions. User experience considerations affect adoption and user satisfaction. Minimize the number of times users must authenticate by maintaining long-lived sessions at the identity provider. Make authentication pages mobile-friendly since many users access applications from phones and tablets. Provide clear error messages when authentication fails, explaining what went wrong in user-friendly language rather than technical jargon. Implement proper handling of authentication timeouts so users aren't surprised when sessions expire. Offer password reset and account unlock flows that work seamlessly with SAML federated applications. Consider implementing Remember Me functionality that extends session lifetimes for trusted devices. Operational monitoring and alerting enable proactive problem detection and resolution. Monitor authentication success rates and alert when they drop below thresholds. Track authentication latency and investigate spikes that indicate performance problems. Monitor certificate expiration dates with alerts at multiple intervals before expiration. Track error rates and patterns to identify systematic issues versus isolated failures. Implement health checks that verify SAML endpoints are accessible and responsive. Create dashboards that provide real-time visibility into Federation health across all identity providers and service providers. Regular security assessments validate that SAML implementations remain secure as systems evolve. Future of SAML and Federation Technologies. As we conclude our exploration of SAML Federation architecture, let's look at the future of SAML and federated identity technologies. While SAML remains widely deployed and isn't going away anytime soon, the identity landscape continues to evolve with new protocols, technologies, and paradigms that will shape the future of authentication and authorization. SAML itself continues to evolve, although slowly. SAML 2.0, released in 2005, remains the current version with incremental updates published as errata and implementation profiles. The OASIS SAML Technical Committee maintains the specification and occasionally publishes clarifications or additional profiles addressing new use cases. However, major new versions of SAML are unlikely. The specification is mature and stable, which is beneficial for interoperability and reduces integration friction. Vendors continue to enhance their SAML implementations with better user interfaces, improved metadata management, and more sophisticated attribute handling, even as the core protocol remains unchanged. OpenID Connect and OAuth 2.0 represent the next generation of federation protocols and are increasingly preferred for new implementations. OpenID Connect provides similar authentication capabilities to SAML but with a more modern, developer-friendly approach using JSON tokens instead of XML assertions. OAuth 2.0's authorization framework enables fine-grained access control and API security patterns that align well with microservices architectures. Many organizations now run hybrid federations supporting both SAML for legacy integrations and OpenID Connect for new applications. Identity providers increasingly position themselves as protocol agnostic, supporting SAML, OpenID Connect, OAuth 2.0, and emerging protocols through a unified platform. Passwordless authentication represents a significant shift in how users prove their identity. Technologies like FIDO2 and WebAuthn enable strong authentication using biometrics, security keys, or device-based credentials without passwords. These protocols integrate with SAML flows where the identity provider uses passwordless methods to authenticate users before issuing SAML assertions. The authentication context in SAML assertions can indicate that strong, passwordless authentication was used, allowing service providers to make risk-based authorization decisions. As passwordless adoption grows, expect SAML implementations to increasingly support these authentication methods as primary rather than supplementary mechanisms. Decentralized identity and self-sovereign identity concepts propose fundamentally different approaches to digital identity. Instead of centralized identity providers, users control their own identity credentials and selectively disclose verified attributes to service providers. Technologies like verifiable credentials and distributed identifiers enable these scenarios. While these approaches currently operate separately from traditional federation protocols, future identity systems might bridge decentralized identity and SAML, allowing users to present verified credentials that identity providers convert into SAML assertions for legacy service provider compatibility. Zero Trust architecture principles are reshaping how organizations think about identity and access control. Zero Trust assumes no implicit trust based on network location and requires continuous verification of identity and context. SAML's assertion-based authentication fits well into Zero Trust models, providing verified identity assertions that access policy engines can evaluate. However, SAML's traditional long-lived sessions may need to evolve toward shorter-lived tokens with more frequent re-authentication and continuous authorization checks. Expect SAML implementations to integrate more tightly with policy engines, endpoint security systems, and context-aware access controls. Artificial intelligence and machine learning are being applied to identity and access management in numerous ways. Behavioral analytics detect anomalous authentication patterns that might indicate compromised accounts. Risk-based authentication systems use machine learning models to assess authentication risk and adapt security requirements accordingly. These systems can work with SAML by analyzing authentication events, attribute values, and usage patterns to identify threats. Future identity providers might include ML-based risk signals in SAML assertions, allowing service providers to make more informed access decisions. Privacy regulations like GDPR, CCPA, and emerging data protection laws affect how identity systems handle personal information. SAML's attribute exchange capabilities require careful privacy consideration, ensuring only necessary attributes are shared. Users can consent to attribute release, and data handling complies with regulations. Future SAML implementations will likely include enhanced privacy controls, such as finer-grained attribute release policies, user consent management interfaces, and audit trails for attribute disclosure. Some organizations explore selective disclosure technologies that allow proving attribute properties without revealing actual values. The long-term trajectory points toward a heterogeneous identity ecosystem where SAML, OpenID Connect, OAuth, decentralized identity, and yet-to-be-invented protocols coexist. Identity providers and service providers will need to support multiple protocols, translating between them as necessary. Understanding SAML's architecture and design principles provides a strong foundation for working with any federated identity technology, as many core concepts like assertions, metadata, trust relationships, and attribute exchange appear across different protocols in various forms. Thank you for your attendance. Please consider subscribing to the channel.